Okay. So last time we started talking about loops, and we were talking about the concept of pre-check versus post-check loops. This was after we talked about Boolean expressions. What are Boolean expressions again? Any expression boils down to a single value of true or false. And we're going to use those all over the place. We're going to use them to form our conditionals, our if statements. We're going to use them in our loops. All right, so we looked at some examples last time. I think we wrote here's our while loop up here. So what I want us to really notice, so while loops and for loops are both pre-check loops, which means that we execute this Boolean expression before we execute the body of the loop even the first time. So if this is false the very first time, we will never execute the body of the loop. So that body of the loop there is not guaranteed to ever execute. All right. For loops are the same thing. Now, I kind of mentioned that the different loops lend themselves to different problems. While loops lend themselves to problems where we don't necessarily know how many times it needs to loop. For loops lend themselves to counting type problems like, oh, we're going to do something 10 times or 20 times or 1,000 times, whatever it is. Do while loops, which we haven't looked at yet, they lend themselves to problems where we have to do something at least one time. They're probably going to be the least common loop that you'll use in your programming, but they still do exist in the wild sometimes. Now, in practice, a majority of the time that we're writing loops nowadays, it's for some sort of counting problem. You know, remember, again, how do human beings solve problems? We remember stuff, we ask questions, and repetition. So these loops fall into that category of how do we accomplish repetition? How do we do something a whole bunch of times? Okay. Well, sometimes we want to say, oh, we want to do something 1,000 times. We want to do something 10,000 times. Or a while loop might say, I want to do something until some condition is met. And maybe that might be 5 times sometimes, might be that 300 times another time, whatever it is. It might just be variable in when that condition is finally met. But something I was showing right here at the end of class, last time we'll review it real quick, is I wrote the same while loop and for loop. So these loops attempt to be equivalents to each other. So reviewing the while loop here is we've defined a variable prior to the loop called count. We started that guy off at 0. Then we asked the question, is count currently less than 10? Right now, count is currently equal to 0. 0 is less than 10. That's true. So we do this stuff. We'll print out the value of count, and then we change the value of count to be 1 greater than it used to be. Loop back up, ask the question again, over and over and over again until count finally is equal to 10. Then we say, is 10 less than 10? It's not, so that's false. We just fall past the loop. We don't execute the body again, and we get to the next line. And right now, what does the next line say to do? It says, oh, just print out the current value of count one time. Current value of count is 10. So this will print out 0 through 10 to the screen. Works fine in a while loop structure. Now, attempting to do basically the identical thing with a for loop, notice with a for loop, all of the same components are still present. If we kind of break down the components up here in our while loop, we have create a starting value, test that value in a Boolean expression, change that value in some way. Those are kind of go-to moves for most loops. We need to remember something. We're going to test that thing or things we're remembering. And then we're going to probably want to change those things along the way. Otherwise, you end up in an infinite loop. You know, if I didn't do that line right there, count starts off at 0. Is 0 less than 10? Yep. Print out 0. 0 less than 10? Yep. Print out 0. 0 less than 10? Yep. Print out 0. Forever and ever and ever. All right. So then you'll have a program that just never ends. So if you have a program that's sitting there and just doing the same thing over and over and over again, when that wasn't what you expected, make sure you're modifying your variable, whatever you're testing against, so that your loop eventually will end. All right. So those are the 3 components we can say of our common counting loops. Define the variable to remember, test the variable with a Boolean expression, change the variable. What a for loop allows us to do, it doesn't require us to do it, but that's more of a syntax truth than in practice. In practice, what a for loop has us do is it has us take all three of those pieces and suck them into the header of the for loop. We are defining the thing we're remembering right there. That part that I have highlighted only happens one time, just like it did for my while loop. We have our Boolean expression here where we're testing it. Then we have our, I haven't actually taught you that yet, but that's okay. Then we have our thing where we're changing the value of our variable. So all those things are brought into the for loop as part of like the package. All right. But it's still the same components that existed before. Now, just real quick, as a reminder, I'm just going to get rid of that stuff real quick. Let me run this first thing. You'll see it prints out as 0 to 10. Okay, there's our 0 to 10 that printed out up top. Now I'll put this code. Oops. Oh, still ninjaing. Nailed it. All right. So now we put this code back in. So we're attempting to duplicate the identical logic from up here inside of this loop. I'm just using a different variable. I'm remembering a different value. So I created a value here called I, and I'm going to tell you why I is a pretty common thing for loops here in a few minutes. So I started that off at 0. Then, because for loops are pre-check loops, we'll ask the question, is I currently less than 10? Is 0 currently less than 10? It is. Print out 0, then 0 becomes 1. Is 1 less than 10? Yes. Print out 1. 1 becomes 2. Notice we only did this variable here one time. We define the variable once with its starting value. That only happens one time as part of that for loop. Then we test. If true, we do this. Update the value. All right. After this loop was done, once we got to I is 10, is 10 less than 10? It's not. We fell past the loop and we attempt to print out the value of I. I think we saw at the end of class last time, it screamed at us. It said, hey, I've never heard of I. Error. I was not declared in this scope. All right, so let's talk about what scope means for a minute. So this is variable scope. I'm going to say where in the program we have access to a variable. So when we define a variable, that variable is available within its own little world. Whatever world it was defined in, that's what governs where we have access to that variable. So if we come back out here, I'm going to go ahead and get rid of this for loop thing again here just for a moment. This variable count is defined inside of main, but not inside of any substructure inside of main. Therefore, count is available from this point forward. So after line 15, it's not available before I defined it, so I can't come before it here and do a cout count like that. It's going to say, hey, I've never heard of that because I haven't actually defined it yet. All right, but it's first available immediately following when you defined it for the rest of main. So as soon as we get to the end of main here, count is dead. Now, right now, we don't have options for where else we might get it, but pretty soon we're going to be looking at functions where we create other things that look kind of like main here, other parts of our program, like we might have something called boy, do something. And if I tried to say cout count inside of there, it's going to say I've never heard of that dude. Okay, because count was defined here in main, so it lived and died starting on line 15 and died here at the end of main. If we somehow get over to this other function here, this guy has his own little scope. You could almost think of it as just a starting point for a rule of thumb, is that anytime you see opening and closing curly braces, there's a variable scope that exists. The funny thing is that we already break our rule here because while loops actually do not have a local variable scope. But at least from a starting point for kind of remembering this, whenever you see opening and closing curly braces, you should at least think, oh, we likely have kind of this new environment that could have variables defined in it. And if a variable is defined in that environment, it's now available throughout the rest of that environment. Go ahead.
So if you define the variable like inside of your while loop, you couldn't take it out.
You still could. Yeah, in this particular case, you could. Although, let's take that as an example. So if you do this inside your while loop, I think actually technically it will work. The logic of this is actually a little funky, but let me show that. Pretty sure it works before I explain why. Oh, it does have a local environment. But now what's even funnier though, oh, it's a pre-check loop. So since this is a pre-check loop, we're asking about count before it was even defined.
So you define like a separate variable inside of there.
Yeah. So if we move count outside of here, and I say, you know, int a is equal to 0 in here, and then I do a cout a, and then I say a is equal to a plus 1, something like that in there. Is equal to 0, less than 10. Why aren't you happy? That's line 30. Oh, because I still have this guy in here. That was the point I was making. Count's not available down there. Notice A is always 0. Because we are defining it over and over and over and over again and resetting it to 0, even though we're changing it right here. This would be stuff you would never do. Just, this is not good programming practice. It's not something that would even make any sense. Just kind of a behavior of this guy. And if after this I do a cout a, yeah, so it doesn't like that, which means that the statement I made earlier is accurate even in old C++, that a variable environment does exist in those opening and closing curly braces. So anything we defined inside of here lives and dies with this opening and closing curly brace. So when we get out here, A is not available because it was defined inside of here and it died when this while loop ended. Whereas count is still available because we defined count outside of the while loop. And since this line is still inside of the opening and closing curly braces of main, it's available. So now along those same lines, that was the TV doing this weird thing again. Along those same lines, we already saw the error here. If I run this from that for loop, it doesn't know about the variable I, because I was defined as part of this for loop. You can think of this as being kind of equivalent to what I did above, where I defined A inside the loop. Technically, this is inside the loop. It's inside the structure of the loop that belongs to this for loop. And when that for loop dies, so does that variable definition. So nothing would keep me then. Let me show you something here. If I say int count is equal to 17 right here, just start with the top part. And I'm going to go ahead and take this out again. See, it's screaming at me. It's saying, look, you are redeclaring a variable that already exists. I already defined a variable in this scope called count. And I used that variable in here a bunch of times. And when I get to line 21 here, count still exists. It's still part of this scope. And now I'm trying to define it again, and C++ is saying, hey, you already have a variable named count. You can't redefine that variable named count. I can change its value. I can say, hey, you're 17 now, but I'm not recreating the memory bucket for holding the value. I'm just saying, here's a new value to put into that bucket that already exists. And now it'll be happy. It'll print out the 17 the last time. So this will be a 0 through 9, then a 17. Okay. So you can change the value of a variable whenever you want, as long as you have access to it. You just can't redefine a variable within the same scope as it was previously defined. Make some sense? Go ahead.
You could use the same name for multiple scopes.
Absolutely. That's where we're going to be going with that variable I here in a second, because you heard me say in a previous class that you should always name your variable something meaningful, right? And we would probably all agree that I is not all that meaningful. It doesn't give us a whole lot of information on what that variable's for. Yet, I'm telling you, it's still a common practice here, and I'll explain why here in a second. Nope, tripping over wires here. Just dump that guy. So here is my for loop again. The scope for this guy lived and died with this for loop. It yells at me if I try to do this, but I could say int I is equal to 17 here, and now it's happy again. Okay. It didn't yell at me that it hasn't heard of I, and it didn't yell at me that I already had I defined, like it did above for count, because I was defined right here. But when this for loop ended, when this Boolean expression was finally false, that definition of I was gone, disappeared. It was as if I never defined it, which allows me then to define I again right here if I wanted to have a variable named I afterwards. Make sense? And you can name that variable whatever you want. This has nothing to do with like I being the special name of a variable. All right. So questions about that? That's really kind of the examples of variable scope. Variables live and die within their own scope, and they're only accessible within the scope where they were defined. All right. Now, I mentioned that for loops are typically used for counting type problems. So all over the place when we write programs, we're going to be doing things like let's repeat something 10 times or 100 times or 1,000 times, whatever it is. We're really using a for loop pretty commonly to just do something some number of times. So when we think about what variable are we going to use for that counting variable, that's kind of a throwaway variable, right? It's like, okay, I'm not storing my age or my batting average or something like that. We're not storing some value in there that the variable name really needs to give meaning to. What we're really doing is we just need a quick throwaway variable to just manage that count from 0 to 10 or 0 to 1,000 or whatever. We really couldn't come up with a better name for the variable. I guess you could call it count. That's fine, but it's a variable that we're just using as a burner variable for right now, and we really want it to die in a second. And the reason why I say that, while I is a nice variable, the common variables are like I, J, and K, because you can have loops inside of loops. So for example, if I put another loop in here, I say int J is equal to 0, J is less than 100, J is equal to killing me, J plus 1. And then I do something like C out J and L. Let's not do the end L there. That way it doesn't get too long on the screen. That'll make it look a little prettier. So I have a loop that's looping through 10 times on I, and then inside there I have a loop that's going to go through 100 times. So for every one time through this loop, This guy is going to go through 100 times and print out J. All right, so we got a whole bunch of stuff that looks like that. So there's 100 times that went through. If I name this guy I, what do you think it's going to say? What's going to happen in this case? Already defined. Because when I get to this point right here and I try to define a variable named I, it's going to say, hey, you are still in the scope governed by this for loop, this outer for loop, and there's already a variable defined named I. Pick a new variable name. Make sense? So it's just so you get the right variable, the right error here. Oh, it actually didn't scream. Just reset it. Well, that breaks what I'm explaining. It's not supposed to happen. Doesn't necessarily surprise me it happens because these so we probably have an infinite loop here because it's never actually, we're resetting it to 100 each time through. So it's actually the scope associated with a for loop. When we talk about in 470, when you talk about writing programming languages and we talk about creating variable environments, there's a full scope. So for instance, a real full variable scope exists with main here. A real full variable scope would exist with like the function we wrote earlier. But the things that are associated with loops, these are kind of like mini scopes. They don't quite work by the same rules, but largely they're the same. Go ahead. That's just for putting extra stuff on the screen to make it look pretty for no good reason. I just gave it some more output. You know, this could be, you know, just printing out hello or something. It's just, yeah, it's meaningless to the code. Why does this let me redefine I? Because if I say int I is equal to a 100 right here, it's going to scream at me. Well, I think what's ending up happening here is what I said before. I actually think it is behaving correctly. It's just the way we're interpreting it is weird. This is a variable scope in and of itself. This is a more local variable scope in and of itself. I think this will show what I want it to show. Let me start this off at 50 and go to 60. And then I can explain this to you because what's happening here is what's called variable shadowing. So this should print out a 0, then it should print out a 50, 51, 52, 53, blah, 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 blah. Actually, let's just keep it less than that. Let's go to 52. So this will be a 0, 50, 51. Well, actually, it'll be 50, 51. Then it'll print out the first value of I. Scroll up here. Oh, that's my while loop up above. So here we go. 50, 51. The first value of I is a 0. 50, 51. Next value of I is a 1. Okay, so this is actually consistent. It is working the way I wanted it to, that it's meant to work. So this whole thing here is a variable scope. This guy right here is an even more local variable scope within that larger variable scope. Now I can have variables defined inside of a more local scope that match something in a more global scope. Hence the reason why it's allowing me to define this variable I when I already have a variable I, because I am in two different scopes there. But now the question is, when I go to print out I right here, which I am I talking about? Am I talking about the guy that's currently equal to 50? Or am I talking about the guy who's currently equal to 0? Well, we saw by the output, we're talking about that 50. Why? It's It's because all variables resolve to their most local definition. This is along the same lines of this scope thing. I'll just create it and I'll get to you in a second. So let's create another slide here real quick. We'll call this guy variable resolution. All variables resolve to their most local definition. This allows us to resolve variables to the correct value when a variable with the same name is accessible multiple times across embedded scopes. Okay. Now, something we would say here is, and the reason I was showing you the J before is, yes, this works, but it's confusing, right? Life would be a lot cleaner if we name this inside variable J, which is going to give us the identical output that we had before. But now we've said, look, when I'm in here, I want to talk about the current value of J. When I'm outside of there, I want to talk about the current value of I. These are two separate variables that I've chosen, and I'm not reliant on resolving embedded variable scopes where we have just happen to have the same variable defined twice and accessible in that scope. It's always resolvable because all variables resolve to their most local definition. So when we go to print out, when we had this as I before, it would say, where was I most recently defined? And it would find its definition right there. So it would use that value rather than this more global one. So we would say that this variable right here would have overshadowed or would have shadowed the one ahead of, above it. Go ahead. Oh yeah. Yeah. You can embed a bunch of for loops inside of each other. Generally speaking, you will rarely see more than, I would say, and this actually relates back to what you were asking before class. Usually when we have a for loop inside of a for loop, we're probably working through a collection type, like either what's called an array or a two-dimensional array. You can have 10-dimensional arrays if you want, but the human brain stops functioning at that point, right? You know, we can think about a list of stuff. We can think about a grid of stuff, right? Okay, that's 2 dimensions. Now, we can probably even conceptualize X, Y, and Z coordinates, like 3D space. All right, so 3 dimensions, human beings can kind of roll with, right? You know, those 3 dimensions, you have X, Y, Z. Z is kind of the depth. But now you get to 4 dimensions. It's not that the language won't let you do it. It's more about like, what are we actually trying to represent with our code? It stops kind of making sense to us. And now all of a sudden you're just like writing a 4-dimensional thing just because you can. And that's okay. But remember, the job of a programming language is to allow us to tell this guy what to do. And once we jump beyond 3 dimensions, if we're dealing with a collection type, we probably no longer really know what we want to do, right? We don't have the ability to conceptualize that. So that's kind of the punchline with that. The limiting factor is our own problem solving in that case, not the language. Language will let you do 200 loops inside of each other, and you want to have there actually probably is some sort of limitation on the array syntax where how many dimensions of an array it'll let you do, but it's got to be more than 3. I don't know. It's been a while since I maybe would have even tried, but in the way arrays are stored, there's no reason why it can't be 100 different dimensions in an array. But we haven't talked about arrays yet, so you don't have to worry about that. It's just a way of holding a whole bunch of crap inside of a single variable name. Right now, we're defining a variable capable of holding a single number. But if I want to hold 100 numbers inside of a single variable, we can do that through a type called an array. And we'll learn about those reasonably soon. All right, so generally speaking, you'll only ever see 3, 4 loops inside of each other. Frankly speaking, that's going to be pretty rare. 2 loops inside of each other is somewhat common, but also, I mean, we're not talking very, very often. You're going to see single 4 loops all over the place. Super, 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 super common. And what you will see, and kind of the point I was going with this before, what you will see very commonly as you're going through your program. Oh, we're gone.
Oh, there we go.
Oh, see, I threatened it.
Yeah.
And all right, so this is something that's going to be more common, and this is why having those throwaway variables is beneficial. I might want to say, hey, I want to do something 10 times right here. And then I want to do something 90 times right here. And they're not inside of each other, but I want to do something 10 times. And then when I'm done doing that, I want to do something else 90 times. Rather than having to come up with a new variable name for that second do something 90 times loop, I can just reuse the I, because I died here. So now I can redefine it no problem and have another for loop using that same counting variable, because I, in this case, is a throwaway variable. It's meaningless in and of itself, other than it allows us to control how many times we're going to do something. That makes sense? This is something you'll see very commonly, where when you're solving problems, we're going to remember stuff, ask questions, repetition. So it's very common in your program that you'll be looping through something a bunch of times, and a little bit later you'll do it again and do something else, and you might want to use the same counter. That way you're not having to do an I, J, K, A, B, C, elemental P, whatever, or having to come up with new names for everything. Historically, if you do everything with a while loop, you could just have your count here at the top, go through and do your while loop stuff, and then you could just reset count to 10 and then say while count is less than 100. That kind of thing. So you'll get the same ultimate effect, but now you have this variable count that's sitting out here in our variable scope here, that outside of this one line right here where I'm using it isn't actually needed outside of that scope. We just had to have it outside of the while loop scopes, but inside of main scope, so that we could use it as this part of this while loop, and then we could reuse it as part of this one by resetting its value. We didn't redefine it. Redefining a variable requires us to put the type in front of it, like that. And right now it'll scream at us saying, hey, you're trying to redefine a variable named count. That guy already exists. Go ahead.
Okay, so I was just thinking, so we define a whole bunch of variables, especially if they have, I suppose if you give the 2 the lower value, but did they ever remove a variable or delete a variable while working through something? Does that make sense?
No.
Okay, I was just curious if that was.
Well, no, it doesn't make sense, is what I'm saying. What are you trying to accomplish?
Well, if the early computers didn't have a lot of memory and counts, but then you needed to get rid of counts to get a different variable, was there a way to get rid of count, or it just wasn't worth it?
Oh, are you saying, was there some sort of intelligent way to let the compiler know I'm done with this variable? It's what we've been talking about today. Let it die with a scope.
Okay.
Yeah. So to your point, the way I have this written right now, let's assume, actually, let's just get rid of all, this stuff here. Let's assume that my last usage of count, I defined count right there, and then I used it inside this while loop, and then I'm done. I'm never going to use count again. So what he's asking is, technically count is still part of my scope. It's still alive. I can print out count right here on line 22 if I want, because I defined it here on line 15. I only used it between line 16 and line 20. But it still exists. It's still taking up system memory, which we don't care about today because we got a whole bunch of system memory. But back in the early days of computers, when memory was really expensive, but we didn't have a lot of memory, he's saying Well, did we have a way of saying, I'm done with this, go away? With variables like this, the answer is no. We did have the, well, and we're going to see them soon. I'm just not going to introduce them yet. But we have these things called pointers, which are variables that hold memory addresses. And what we can do is we can then delete that memory when we're done using it. So there is a way to accomplish what you want to accomplish, but we have to look at a little bit different type of animal here. Very similar. It's a close relative of this guy. But yeah, and part of the reason pointers existed was for that memory management type stuff, but it also has a whole bunch of other benefits that we're going to see. Go ahead.
And just like add code basically to declare new scope.
I don't think so. I mean, so let's just go down that rabbit hole real quick. Because technically that's allowed. You can just put a block statement, because this is a statement. You know, when you have a like our main here, and you have the opening and closing curly braces for main, you don't actually have to have that. Main will execute the statement following it. I'm going to say, hey, I might want to put a whole bunch of statements in there. So I'm going to use a block statement, which is a kind of a garbage bag capable of holding a whole bunch of statements. Well, since an opening and closing square or opening closing curly brace there is a statement type, nothing keeps me from saying, let's do int woot is equal to 5. See out woot. Bill. And then I'll try to print it again after that. So I believe that woot will still be accessible here. This is an interesting question because I earlier advertised that, hey, what if we have, I said, every single time you have an opening and closing curly brace, you can probably assume that's a new scope. And there's a pretty good truth there, even though we've kind of seen a little twists and turns with some of those rules. When you just have a block statement out in the middle of nowhere here, I'm thinking how the language would be written. I don't think having just a block statement not attached to one of our structures, like a function, a loop, something like that, I think it's going to let us use woot here. It did not create a new scope. So let's see. I'm going to go ahead and test it. But I had told you before, don't run a program until you've at least made an educated guess of how you think it's going to work. All right. So I believe this is just a standalone block statement, not attached to a loop of any kind or a function of any kind. Therefore, a new scope would not have been created. So technically, this woot variable belongs to the scope of main. Therefore, it's definitely going to be accessible inside these opening and closing curly braces, but I believe it'll also be accessible here. It will not have died at the end of that opening and closing curly brace. Let's see if I'm right. Not declaring the scope, line 26. So even solidifies what I said earlier. Every time you see an opening and closing curly brace, it's a new scope. It's very interesting to me. I don't feel like that is how it has always worked with C++. But it's actually good. That's more consistent. Anytime you see opening, closing, curly brace, that's a scope. Okay. And of course, I did that on purpose, for educational. All right. But as a programmer, that is the type of stuff you'll do. You'll say, oh, and in this kind of thing, we're kind of trivially saying, oh, well, can I do this? Can I do that? Whether or not we would ever actually want to do that is a whole different discussion, right? But it's interesting to say, well, can I? Can I accomplish that? So we just ran a little experiment, right? We tried to do it. We saw what happened. We tried to understand the behavior, moved on with life. Okay. Questions about variable scope stuff. Make some sense? All right. So now we know about how to remember stuff. We know about how to ask questions. We know about how to do repetition, right? We know about those 3 things. Haven't written functions yet. We'll get to that. That's kind of a secondary way of doing repetition. Don't worry about that for the moment. But we want to introduce a new type. And this particular type we're going to introduce is really, really, really commonly used in computer programs. And I think we're going to see here, especially some of the evidence today suggests that we are dealing with a significantly updated version of C++, which isn't a problem. That means it's behaving more like our more modern languages. This is a good thing. It's still going to be a little cryptic when we get to pointers. And I'm going to show you that example here in a second. But we have something called a string. So we have the string type. Okay, strings use an opening curly brace, and then, some collection of characters followed by a closing curly brace. That's an example of a string. Okay, it's a bunch of characters, 0 or more characters surrounded by double quotes. Now, strings are super commonly used in modern programming. Old school programming, where memory was at a premium, we pretty much stuck to numbers, but that also limited us on what we could actually accomplish with the amount of memory we had. It wasn't that we couldn't use strings in older programs. It was that there were not quality of life ways of using strings. So we have something called an old style C string. And this was done through something called a pointer. Got this guy here. So I could have said something like char pointer s is equal to hello. Let me make sure that this guy's cool with that. And this guy, okay. Just give me a warning. See it. It's a warning, so this technically is working, but it's letting me know there's a newer way of doing this. So what I would have to do then, malloc is let's just say 1,000 here. Malloc is probably in a different library. It's gonna yell at me, maybe. No, we're good. All right, so malloc must be maybe inside standard namespace. I thought it was in UniSTD, but whatever. Then I'm gonna say s is equal to hello. Oh. So it wants me to use string copy. Okay, well, this is still showing me my point. The point I was making is that old style C strings, the language didn't have all these quality of life things built into it. So what I did here is I created a variable named s, and this variable is capable of holding something called a char pointer. Pointers, let me just introduce that here. These are variable types capable of holding a memory address. That's what a pointer is. Just like an int holds a whole number, a char holds a whole number but means a character, right? A float holds a decimal point value. A pointer type, and the syntax we had for pointer was just throwing the little asterisk guy after that. All right, so I'm creating a variable named s of type char pointer. That means it's capable of holding the memory address of a char. That is to say that this variable will point to where a char lives in memory. And just to show that to you, if I say cout s here, you're going to see weird memory address things stored inside of s. Not going to actually show me the variable address. No, it should show it to me. You have a question? I'm showing you the old way of doing it. We're going to look at a newer way of doing it. In fact, it's making it inconvenient to do it the old way, to be honest. Okay. Whatever. This would have shown us a weird, I can probably force showing you what the memory address looks like if I say int a, and then I say, let's go int a equals 5. And then I see out the address of a, hopefully that'll let us see a memory address. There we go. So memory addresses look kind of like that. Some big hexadecimal value. Remember when we were talking about the different number conversion stuff, I mentioned that for human beings, the way we think about addresses is really complex, right? We have a street number, a street, a city, state, all that stuff, where in a computer, all your stuff lives on one big long street. All right. And this variable we created here, a, of type integer, that we put a 5, this 5 is inside of a bucket of memory way, way, way down this street at that location. If we converted that to decimal, it would be house number bazillion, you know, whatever that converts to. Okay. When I created this char pointer up here and I allocated memory for it, that's what malloc does. I'm saying, give me 1,000 bytes of memory for holding this char pointer. And what that's going to do is it's going to go and create 1,000 bytes in a row of memory somewhere in your computer. And then I can then start putting stuff in there. But because this is an older version of, well, these are old style C strings. When I went to say S is equal to hello, like this, it screamed at me and said, you can't just put that directly in there. It did give me a warning though, so I wonder if it'll still hold it. Yeah, it did still hold it. So it still worked. It was just giving me a warning saying, look, this is not the way to do it now. Okay. If you know the little trick under the hood, if I set it to that, it's only going to print out the hello. And the reason for that is in old style strings, the string termination character is a \0. See, I created enough memory, like I built a house. This line right here builds a house capable of holding 1,000 characters. That's what I did right there. I asked the operating system to allocate some memory for me big enough to hold 1,000 characters. Now, I didn't put 1,000 characters in here, right? I put way less than 1,000 characters. But when I originally had just hello put in here, what it actually stored was hello with a \0 at the end of it. That was the string termination character. Cout uses that when it goes to print out the current value of S, it's going to start at the base address, whatever S holds, some memory address, and start walking through it character by character, displaying it to the screen until it hits the end of that string. And it thinks it's at the end of the string when it hits a \0. So I can screw with the computer here by saying, okay, hey, I'm going to go ahead and give you a string to store, hello. And I'm going to store hello world, but you know what? I'm going to mess with you and just throw the string termination character there in the middle. It's also putting the string termination character at the very end for me. It automatically is putting that in there for me. It didn't know that I went and hijacked it and threw the string termination character even earlier in it. So when I went to print it out, it only got to the hello because it hit that \0 right here, which is string termination, which says, I'm not going to keep going and find the world. If I take this guy out and just put a space there, let's say now I'll get the whole hello world. Make some sense? So this is more of a old school trivia thing that the string termination character historically was a \0. We're going to be using new style strings, which make life a little bit easier. And the reason why it's still giving us the warning here that, hey, this isn't how you can't convert a string constant So it's saying, hey, this guy right here, what I wrote, this guy is a string constant. That's the kind of value that is. And it's saying, hey, you can't just put a string constant into a char pointer. They want you to use something called string copy. I think the S comes first. And that might be in string.h. Yeah, it's inside of string.h. But whatever. This would be a function that exists that would copy this string into this variable. And then it would not yell at you once you had the right guy included. Go ahead. Yeah, see, it's not screaming at us anymore. Malloc is memory allocate. Yeah, and you don't have to really know that for right now. We're going to talk about that a lot more when we talk about arrays. So really, this was me showing you that strings used to be a little bit more difficult to deal with. Yet we kind of want to work with strings pretty often, and they're going to be helpful for us. And this is actually related, if you remember, when we first looked at main here, we had an int argc and then a char pointer argv. This is an array of strings, and this is the number of things in that array, because arrays aren't, historically, we're not able to advertise to us how many things were in them. Okay, so old style C and C++ did not have some of those quality of life features, so we had to do all this extra crap. If I wanted to store a string, I had to allocate some memory for that string, and then I had to use another function to copy each of these characters into this memory location that I had previously allocated. I couldn't just toss it in there. Well, I could. It just warned me and said, hey, this isn't the way it usually works. Go ahead.
I was just gonna tie off your the \0. For some reason, you want to store hello \0 world. Did you escape that?
Yeah, you can.
Okay.
Well, actually, that's a good question. I think you would do it like that.
Okay.
Yeah. Okay. And now we're getting into some like weird trivia stuff here. It's not that these things are unimportant. These are just things you're likely not to run into very often. This is called our escape character, the single backslash. So if I want the best use of this is, let's say that you wanted to have a double quote in the middle of your string. Double quotes are the beginning and ending portion of how strings are represented. But if I want to actually hold a double quote inside of my string as part of the value of the string, I have to make sure I'm letting C++ know that I don't intend for this to be the end of the string. I intend for this to be the actual character double quote that I want to appear in the string. So we can use the backslash symbol here to do what's called escape that, which says whenever you hit the backslash character, it says treat whatever's next as whatever it is. Don't try to interpret it. So this will put the double quote there in the middle. Make some sense?
I was playing around with one of the reasons for copy. Oh, okay, that's like okay, I was like.
Yeah, so I mean, now we're getting to some pretty old C libraries. There's a library out there called string.h that has a whole bunch of crap in it, functions for dealing with old style strings to give us a little bit better quality of life, but it still kind of sucks, is the point. Make some sense? All right. But for us, we're going to be using a new style of string. So I'm going to say, I think it's lowercase s, string s is equal to hello world. I'm going to go ahead and take string.h off. All right. That nicer? I didn't have to allocate any memory or anything. Now, having said that, allocating memory is important. And we definitely are going to look at it a lot closer when we get into looking at arrays or collection types. So I don't want to toss it out the window and say, oh, you'll never have to deal with allocating memory. For any of you who've used any of our more modern languages, anytime you use the keyword new, like in Java, if you say random R equals new random, anytime you say the keyword new, it's asking the operating system for new memory. New is the modern day version of malloc. So it hasn't gone away. We still, as programmers, have the ability to request the operating system to create a bunch of memory for us. And we'll look at that in a lot of detail when we get to arrays. But I'm going to make the argument that, you know what? Strings are a pretty common thing that we like to deal with. Let's not make it a headache and a half for us to deal with strings. Make some sense? Okay. Good.
The stuff that arts and RGBs basically just define this memory space for this program.
Yeah, remember we did the command line arguments? This is how we like read in those if you wanted to feed it stuff from the command line. It's not required in C++, but if you did want to take in command line arguments, you need both of these things. This is a collection of strings that you would take in, and this is how many it found. Yeah, but modernly, we typically, when we write programs, we don't use command line arguments, but we saw that any sort of Unix command, I use the editor like VI, and I gave it test.cpp, I think was like the name of the file I used. It needed to know what file I wanted to edit. So those are examples of where command line arguments make sense today, or make sense back then. But today you would just open up Microsoft Word and go to File, Open, and go and find your file, and life goes on. Or just double click the file. And then it's MIME type knows to open up Microsoft Word, and you're off to the races. But I still make the argument that these things are important things for us to have in the back of our mind. You don't have to memorize all these things. I'm not going to test you on specific things here. One thing I do before the exams is the class before the exam, I'll go through the slides and I'll tell you what things I think are important and what things you could ignore. So you'll have a good idea. I'm not going to, my goal on an exam is not to trick you. I want you to show me what you've learned. And if you can pick up 20% of some of this older stuff, that would be nice, because then you have some of that foundation. Almost think of it like a car mechanic. Some old guy who's been working on cars since the 40s. He might know some stuff that, like, oh, well, you just wiggle the carburetor this way, and you just put just a little bit of vegetable oil on that, and it'll work. Just, you've got these weird hacks, right? Where a modern day, car mechanic knows how to plug the computer into it and does like the self-diagnosis thing. We'd like to maybe be somewhere in the middle. We don't need to go all the way back to the invention of zeros and ones, but to know some of the stuff that all of our modern computing is built on top of it is pretty important for us as problem solvers. Go ahead. Well, it's going to be in the videos. What I'll do is at the end of class, when I have like examples of string stuff, like the way we're going to do it, I'll put that up. Yeah. Yeah, usually, well, no, I usually put on Slack. Yeah. But the videos are always up, so you can go through and pause the video and see it, all that stuff. Okay. So modernly, if we want to store a string, we don't have to do anything special than we did before, because the string, it's called a class, the string class lives inside of the standard namespace, just like cout does. Okay, so if I want to store a string, it's string. That's the type. You put a string in front of it, then your variable name, and you put your string in there, and it doesn't scream at you. Everybody's happy. Takes way less time, but it is less cool. You feel less geeky. Just interested in how much they protect modern strings. Yeah, now let's get to the memory. So here's your evidence. The crap we just did a few minutes ago, it's still there. Under the hood, that's what this dude is doing. It's saying, okay, you want to store a string? I'm going to go ahead and allocate some memory for you. And then you tell me what you want to store in there, and I'll go ahead and string copy that in there for you. So it's there. because when I went and printed it out and I said, you know what? Don't give me the value of S, give me the address of S. And it showed me where that guy starts. So it's in memory, somewhere down the street, and we can get to it. This is actually something that's missing from most of our modern languages. Java does not have a special syntax for pointers, doesn't let you get at the memory of things. There's a couple different ways you can see the memory address of an object type in Java, but it's meaningless to you. You can't do anything with it. It's more just an interesting type thing.
You more so like trust the compiler to know how long you need it. You're not wasting memory.
Well, wasting memory is probably less on its priority list, but let's say yes, that's a true statement. I'm already on this guy. Let me hide this. So this is the modern string library. And I can I'll paste this on Slack real quick. Here, if you notice, I put up some pictures. There's Mr. Gonzalez with his airplane ticket. He gets his own seats on flights. So there's a link to some C++ reference stuff. All right. So this is a type that exists, and it is a char pointer still. It uses something called a type def. You can invent your own types in C++ historically. There's a bunch of stuff we can do with strings. Let's just go down here, and we can ask a string what its size is, or its length. Length is probably, I bet you they do the same thing, but okay, so this is a length function. So I can say, here's the value of S. And there's the length of S. S is 11 characters long. So a string can report to me how long it is. So I defined my string here, hello world, printed out the whole string, just showing you can. Then I printed out what the length of that string is, showing you this is how you can access the number of characters in a string. Then I used the for loop. So I'm going to write a loop. I'm going to start I off at 0 because strings are what are called 0 indexed. The very first character of the string, this H, this is at bucket 0. Bucket 1, bucket 2, bucket 3, bucket 4, 5, 6, 7, 8, 9, 10. So yes, this string has 11 characters in it, but the legal buckets, the legal locations of those characters are 0 to 10 to give you the 11. So what I did is I wrote a loop here that takes I on a journey from 0 all the way up to, but not including in this case an 11. So this will go from 0 to 10. Okay, so, you know, if I just print out I in here, this is going to print out a 0 to a 10. Same loop we had before. There's my 0 to 10. But I can choose to use that value of I. Instead of just printing out a 0, I could say, you know what? Give me the character that you found at location I in that string. Give me bucket 0, which is an H, bucket 1, an E. And I'm pressing enter at the end of each of those lines. So this is going to show me each character of my string, one character, one line at a time. There's my H, my E, the L, the O, so on and so forth. If I don't put the end L on there, it's just going to put them all right next to each other, and you won't be able to tell the difference between the two lines. So here's me printing out S directly. And here's me technically printing out S one character at a time, but not pressing enter between the characters. But they're still getting out to the screen one character at a time rather than the entire string at once. Okay, so this is how we can get the length of a string. So strings have a bunch of things available to them that allow us to solve problems. So we'll say, this is a lowercase s. We have string functions. So this is length. Reports the number of chars in a string. Go and look at what else we have. That's going to be useful to us. You can get max size because when it creates a string, it's going to go ahead and just grab a whole bunch of memory. Modernly, it doesn't care about the memory, so that's probably not overly important to us. We can adjust the size, blah, blah, blah. We can empty out a string, probably not something you'll use either. Yeah, so we're going to look at string concatenation. That's going to be a pretty handy one as well. So what I'll do here, and actually that's done through a, I'm going to create a string S2, and I'm going to start that guy off as the empty string. Okay, so S2 will be, the starting point is it is a string that has 0 characters in it. And I want to add some stuff to that guy. So what I'm going to do is I'm going to go through every character in S, but I'm going to skip every other character. So I'm going to add 2 to I each time. So I'll do bucket 0, bucket 2, bucket 4, so on and so forth. Now, if I just print these out, you'll see it's only going to give me some of the characters, the H, L, O, W, R, D. Yeah. Lowered.
Your brain auto.
Yeah. All right. But what I'm going to do now is I'm going to, instead of printing stuff out, I'm going to build up my string S2 with those partial components of S. So I'm going to say S2 is equal to whatever S2 currently is. I'm going to put the plus sign there. This is going to be the concatenation operator. S at bucket I. I'll do a C out S2. So this is my S2 now. So S2 started off as it is a string. So the type of animal S2 is a string. And I gave it an initial value of the empty string, a string with length 0. Still a string, just has a length of 0. If you want to see that, we can do a C out S2.length. There's the length of S2 is that 0 there at the beginning. Okay. It's a string, just doesn't have anything in it. All right. Now I'm going to go through every character. Well, I'm going to go on a voyage taking I starting at 0 up until, or as long as it's less than the length of S. Remember, S has a length of an 11. But I'm going to have I skip by 2s. It goes 0 to 2 to 4 to 6, so on and so forth. But what am I going to do inside the for loop each time through? I'm going to say, okay, here's my S2. I want to expand S2. S2 started off as the empty string, so I want S2 to equal whatever it currently is. So the first time through, that's the empty string, concatenated with the single character you found at position I in S. So I'll go ahead and grab the H. So now S2 is equal to just an H. If we want to see it as it's being built, we can see S2 being built up here. So there's the H, there's the HL, there's the HLO, HLOW, so on and so forth. Okay, so the work that I'm doing inside of this for loop is meant to build up S2 with part of S. I'm skipping some characters. All right, that makes some sense. All right, so this plus sign here, we typically recognize the plus sign as addition. We want to do mathy stuff. But the plus sign, when associated with strings, is the concatenation operator. It glues strings together. So for instance, I can say string S3 is equal to hello plus, I'll put the string arrow in there for no good reason, plus whatever S2 currently is equal to. And then we'll do a cout S3 and L. So I'm going to glue a bunch of these things together. So I'm going to glue the string hello, followed by an arrow, followed by this lowered thing. And that's what S3 will end up holding. It's not like we do multiple at once. Well, that's interesting. This is why. Should have just used my variables. Is it running? Not even running it. Oh, there it is. There we go. So then I can throw in my there's my hello arrow, hello lowered. Now the reason I have to do this is because C++ is a more modern version of itself. If I just put hello like this, the double quotes, C++ doesn't know, hey, do you mean a new style string or an old style string? So me putting string in front of it like that, saying, treat this guy as the new style one. Punchline here, though, is the plus sign when you have strings on either side is for working with gluing these guys together. Homework assignment for next class. I'll put this up on Blackboard and I'll give you the code I did in class today as kind of some sample code. Is create a program that sets a string variable to something and displays that string in reverse to the screen, and also builds that string in reverse inside of another string variable. So for example, if you had hello, it should output OLLEH is what should show up on the screen. And then you probably are going to have another variable like our S2 or something like that, which is going to show the same thing. So maybe it's like S2 is equal to OLLEH, something like that. So walk a string backwards. You're going to have to do some modifications to your loops, that kind of stuff. Questions, comments, concerns, bribes. All right, I'll see everybody on Tuesday.
So first of all, thank you.
Mm-hmm.
And also, so for the first homework, I'm actually only able to start on it right now today because my computer was like stuck on the home screen and like I got it to work, but then I had to, and I was working on it. But then
You mean the original program, or are you talking about the program that was due Tuesday?
yes,
Okay.
and
I mean, you can use any computer that has a web browser. I mean, you don't need your home computer to this.
yeah, I just have it.
Okay. Well, I mean, like there's a lab right on the other side of this wall.
Oh,
You can
yeah.
go into and use a web browser in there. All right. So get it turned in. but let's start getting stuff in on time, all right? Sure.
If you have a string with a length of one character, is that indifferent?